Hopefully you had a good weekend. We're back at it again with another video. Today we'll actually start section 9.3. We don't need to know 9.1 for the AP test. I will give you a Reader's Digest version of 9.2, which is kind of like an introduction to parametric equations. There is no calculus really in 9.2, just gives you an idea of what parametric equations are, which I will do as well. And then I'll actually talk about section 9.3, which hopefully you have the notes for right now. It talks about parametric equations and the calculus that you could do with them. So just like we did the videos last week, if you want to start with this warm-up, we can pause the video, give everybody a chance to try it and see what happens. So if f and g are twice differentiable, and if h is defined as f of g, then what is h double prime of x? So if you can pause the video, give everybody a chance to try it. Which one of these answer choices are you going with? All right, hopefully you had a chance to try it. So in terms of solution, the answer was A. How you go about it is, well, it's going to be the chain rule, right? We know that in this case, if we start with h as f of g, then h prime is going to be f prime of g times g prime. If you take a derivative of that, you're going to run into chain rule and product rule. So in this case, you could argue it's two chains. There's a joke in there somewhere. So if you run through my work here for h double prime, you'll see the reason why I have plus is because I'm doing the product rule, and I also got some chain rule going on as well. And at that point, you have two g primes, so we know that that's g prime squared. So then this is the reason why answer A is a good selection. Okay, feel free to pause the video if people want to look at it or jot it down or talk about it. Otherwise, we'll dive in. So at the end of last week, we talked about section 8.10, which was Taylor-Maclaurin power series. We talked about developing Taylor-Maclaurin for the last several sections. And then the last conversation we had was, what about a binomial series? Could you write a binomial as a power series? Which we did. And then we did say there were some ones that were worth your time knowing, such as sine, cosine, e to the x, natural log, and that binomial, which was the quantity of 1 plus x to the k. That being said, how about section 9.2? Again, 9.1, not something we're going to be responsible for. Section 9.2 talks about plane curves and parametric equations. Again, we're not going to take too much notes on them. I just want to give you an idea of what they are before we start doing some quick and easy calculus with them. So not the most labor-intensive thing that we've done, which is kind of a good thing here at the end. So let's talk about it this way. So the first thing that comes up in conversation in the notes for 9.2 is something called a rectangular equation. And it turns out that rectangular equations are the equations that we've been seeing all along. The equations that have y's and x in them. Again, we always say y equals something in terms of x. So the reason why it's called rectangular is because in the xy plane, you could have an x coordinate and a y coordinate, and that would actually give you a rectangle from the origin. So imagine that you have the regular xy plane. We know x goes side to side, y up and down. If you were to pick a point in the first quadrant, whatever that point is, we can say it's, x sub 1 over, maybe y sub 1 up. You could actually build a rectangle from that point to the origin, and this is the reason why it's called rectangular. So if you see something about rectangular equations, just think about the regular equations that we're used to since algebra 1, y in terms of x or x in terms of y, but most of the times y equals something in terms of x. But it turns out there's another way that we can describe it, kind of in like a physics kind of a approach. I don't want to use that word too much because I know some of you guys have mixed opinions about it. But what I would say is that parametric equations are kind of friendly because what they'll do is that they allow us to talk about motion in terms of components that are side to side and up and down. So let's say we were to take a ball, let's say a tennis ball, and I was to throw it up into the air. Well, that ball could move side to side. It could also move up and down. So in this case, you could talk about a vertical component, how it moves up and down, and a horizontal component that moves side to side. So the nice thing about parametric equations, what it allows us to do is it talks about the variable that's working behind the scenes. So if you think back to first semester when we were doing things with related rates, remember that there was one variable that you could always kind of relate to when you're talking about different things changing, whether it was like a volume and a radius or a diameter of something changing. The thing that was changing behind the scenes that kind of correlated everything together or connected everything was time. So it turns out that that's the parameter in this case, what's behind the scenes. and allows you to break up the components separately, so that if you wanted to talk about specifically how an object was moving horizontally, you could talk about its horizontal component in terms of x and time. If you were interested in how the object was moving vertically, you could talk about the vertical component and then isolate y in terms of time. So this is what a rectangular equation would look like for this kind of an object's movement. Again, it starts at the origin. It looks like it goes upwards and then comes back down to the origin. You can see kind of by the arrow in which direction it's traveling. We do know it's parabolic, so we would expect the rectangular equation to have something with x squared in it. If you look at the coefficient in the front, you could argue that's negative 1 over 72. It's negative, so that means you have a downward facing parabola, and it is kind of spread out because this a value, negative 1 over 72, is kind of a small value, so we'd expect this to be kind of a wider parabola facing downwards. But if you break it up into its components separately in terms of horizontal and vertical, you can actually see here the parametric equations. That's what it means to break up components into horizontal and into vertical. You can see that x in terms of t could be this way. So if you wanted to talk about how an object was moving side to side horizontally, you could talk about 24 times the square root of 2 times t, which is time. If you want to talk about object's vertical components, then you could talk about how is y changing with respect to time. And what's kind of nice about this is that it kind of isolates the movement that you're interested in. In the case that you weren't interested in just isolating maybe the horizontal or the vertical, then you could talk about the rectangular equation, because now that's relating how horizontally is changing with vertically at the same time, rather than talking about the time component that's kind of changing behind the scenes. So all of this is just a fancy way to say rectangular relates x's and y's, kind of like what we've been doing for a long time. And the new nice part about parametric, it does allow you to isolate by component if you're more interested in a horizontal or a vertical movement. So, okay. So then what does the book say about it? So the equation does not tell you the whole story. However, it tells you where the object has been. It doesn't tell you when the object was at a given point. To determine this, you can introduce a third variable, t, which again is time hidden behind the scenes, which is called a parameter. Again, for those people that are in the stats class, we've seen some different parameters before as well. By writing both x and y as functions of t, you can obtain the parametric equations. From this set of equations, you can determine where the object is at specific values of t. For this particular motion curve, x and y are continuous functions of t, and the resulting path is a plane curve. So nothing crazy there. You can look at the definition of a plane curve. Basically what it's saying is if you take an object and break it up into its components of movement horizontally and vertically, since they're both with respect to time, if you were to plug in a time component into both, it would tell you the location where something is horizontally and vertically at the same time, which is very much like what we do in rectangular equations. So again, here's another example of kind of like something with movement. So if you're looking at the rectangular equation, we're very familiar with this one. 1 minus x squared is a downward facing parabola, just up 1 unit. But if you were to break it up into its parametric components, you could also see that we could talk about each one separately. And if you look at the movement, one extra kind of nice thing about talking in terms of parametric is you can look at the arrows indicating where the object is moving. So in this case, it'd be moving from left to right, or actually from right to left, it would be moving upwards. So just kind of following the arrows, where if we look at the rectangular equations, it doesn't really tell us. We just kind of go with x's, and as x's increase to the right, we'd imagine the function goes downwards. So in rectangular, it's kind of indicating the arrows would have been the other way. So that's another nice thing about parametric, is as you plug in t values, it actually will tell you, based on what comes back to you, which direction you're traveling. All right, the last thing that would have showed up here is something that's kind of famous, so I wanted to mention it. Not that it's super important for what you need to know about calculus, but it's something called the Touchstone problem. So basically what that is it talks about pendulums. So if there's something that you're interested in with pendulums, you want to know more about it, feel free to take a picture. You could take a look at it. It talks about Galileo and a very famous mathematician Huygens, who actually did some great things with pendulums. In his work in math and science was something that was revolutionary, and he kind of built it from Galileo. I think just Galileo found out about it a little bit later in his life. He was trying to discover some things and just kind of ran out of time, but then a bunch of people picked up his research and kind of took it from there. So if you're interested, it's kind of an interesting idea definitely something you can look into if you want. And it's definitely tied into parametric because you can talk about pendulums changing in terms of their components, both side to side and up and down. And there was a big discovery. If you want, you can pause the video. You can read this if you like, or you can just take a picture, read at your own time, or do some self investigations if you're interested. Okay, so then how about for us? We have notes section 9.3 hopefully in front of us. So it talks about these parametric equations based on the breaking up by components, side to side, up and down in terms of time, and the calculus that we can do with them. So what is the calculus that we should be able to do? Well, we should be able to take derivatives. We should be able to talk about the rate of change of a horizontal component or the rate of change of a vertical component. So here it gives us two parametric equations. It gives us something for x, something for y. Notice they're both in terms of t. It talks about what's happening with the object. So our projectile is what they like to say, is like a fancy way of saying an object. Projectile just means that it's something that's put into motion. So that would be something to consider. So it gives us a picture for what this would look like in this specific case. And we can actually talk about how the components are changing. So here it says, what is the parametric form of a derivative? So we see our familiar notation dy dx, but it also talks about dy dx in terms of the components. So notice how we can make up the derivative. We can find dy dt, which is the derivative of the y component, or the rate of change of the component that moves up and down. And we're going to divide it by dx dt, which is the rate of change of the horizontal component, which how something moves side to side. So if you wanted to include in your notes, one little quick thing. So it actually is not that bad. We don't have to do any quotient rule or anything crazy like that. To find this part, which I'll just kind of bring off to the side, we can say take dy dt, so just the derivative of the y component with respect to time, and divide it by dx dt. But a cool thing happens if you divide by dx dt. We know that dividing by a fraction is the same thing as multiplying by its reciprocal. So rather than dividing by dx dt, we can multiply by dt over dx. So we'll actually see the dt's are going to cancel, and you'll be left with dy dx, which is traditionally what we know as the derivative. So it's really nothing crazy. We don't have to do anything in terms of a quotient rule. We just need to take the derivative of each component separately and then divide them. So let's see a couple examples. Let's see this in action and see what happens, see what kind of trouble we can get into. So here it says find dy dx for the curve that's given by x equals sine of t and y equals cosine of t. So again, I know we just mentioned it, but if I was going to try to find dy dx, if it was just regular rectangular, then I can take the derivative as normal. But since I'm doing things parametrically, I need to do things with the regular components. I need to find dy dt, and I need to divide it by dx dt. And we did show that the dt's would actually cancel out, so you're left with dy dx. So let's just go to the components. I know x is equal to sine of t, and y is equal to cosine of t. So I would start with y equals cosine of t and say, well, what's the derivative of cosine of t with respect to t? Hopefully somebody said out loud that the derivative of cosine is negative sine, and it is in terms of t. All over, we need dx dt. I know x is sine, so then what's the derivative of sine of t with respect to t? It's going to be cosine of t. So then if I was you, I might try to simplify this. Well, I see a sine over cosine. I know that it's negative. I know sine over cosine is tangent. So because there's a negative out front, I would say this is going to be negative tangent of t. So maybe to sum up the first piece, we can say dy dx is equal to negative tangent of t. And that would be dy dx. So then in this case, that would be the answer for the first piece. But I want to do a little bit more with it, so hopefully you still have a little bit of space there. You could also take other derivatives. So just like in rectangular equations, we can take a second derivative. We can take a third derivative. Let's quickly take a look at the second derivative, because there's something about parametric that's a little bit different than doing things in rectangular, which kind of makes sense since we're breaking up into components, and we know that t is kind of behind the scenes as a parameter. Then they might be a little bit different than what we do in rectangular. So you can see here the notation for the second derivative. We don't actually need to know the third derivative. It's not something that shows up in conversation. Never something I've seen asked of on the AP test. But how about the second derivative? I have actually seen that as a question that has been asked. So it says if you want to take the second derivative, then take the derivative of the first derivative, of course. So then how do you do it? It says take the derivative with respect to time of the first derivative and then divide it by the original dx dt. So I would say the top part, it kind of makes a lot of sense, is you're taking the derivative of the first derivative, which makes sense for a second derivative. But the part that makes it kind of interesting is that you still have to divide by the original dx dt. So going back to this example, I kind of want to extend it. I know that they just asked us for only the first derivative, but I want to find the second derivative with you because I think that that would be helpful or beneficial. So just remember that the first derivative is negative tangent of t. So let's write down the second derivative. So let's use the notation. So then we know the notation for a second derivative is going to be d squared y over dx squared. And then how do we find it? So we got to take the derivative with respect to time of the first derivative. The first derivative we just found was negative tangent of t. And then we have to divide it by the original dx dt. So then I will just write that here. So then we'll write another line. So it looks something like this. So then what is the derivative with respect to time of negative tangent of t with respect to time? So does anybody know the derivative of tangent? Hopefully somebody said secant squared, and it is negative. So this will turn into negative secant squared and then of t divided by, well, if we divide here, we need to divide by dx dt. So then what did we say about dx dt? We know x by itself is just sine of t. So dx dt was cosine of t. So it looks something like this. Now that would be okay as a final answer, but I think we can go a little bit further. So maybe we can say something about this negative secant squared. What's another way to say secant squared? Remember, secant is the same thing as 1 over cosine. So secant squared would be the same thing as 1 over cosine squared. So if I just wanted to write negative secant squared of t, I could write negative 1. It's a negative because that's a negative secant squared, and it'll be all over cosine squared of t. Now instead of dividing by cosine, I could say multiply by 1 over cosine. So it looks something like this. Hopefully you'd agree, fractions multiply straight across. So I think what we're going to have is going to be negative 1 over cosine squared times cosine. This is going to be cosine cubed. So then last but not least, maybe I just rewrite it. So I can say this second derivative in a nice clean version would look something like this. And I have negative 1 over cosine cubed. Well, I know that 1 over cosine cubed is secant, so because it's cubed, it's going to be secant cubed, and it will be negative. So then I know the example doesn't ask for it, but I think it would be kind of helpful to know because I have seen this as a question, and not that it's terribly difficult, it's just a little bit different, and something to definitely mention. All right, so I think that's example number 1. Again, feel free to stop the video, chat about it, rewind it, whatever you guys need, but I think that'll do it. So let's keep rolling. I got a couple more examples I want to do with you. So how about example number 2? So example number 2 gives us two parametric equations. Gives us something for x, gives us something for y. So then it says to find the slope and the concavity. All right, so to find slope and concavity, well, hopefully you'd agree slope just means the first derivative. Concavity would definitely have something to do with the second derivative. So a good place to start would be, let's find a derivative and see what happens. I do see that x is the square root of t, so if you wanted to, you could say, well, that's the same thing as t to a 1/2 power, and then we do have y is equal to 1/4 times the quantity of t squared minus 4. Okay, so let's handle the first question of slope, and then I'll have another slide for concavity so that I have enough space. So don't write too big so you can try to fit everything. So then how about the slope? So to find the slope, I'm going to need a first derivative. I know that for a first derivative, I should take the derivative of the y component with respect to time and divide it by the derivative of the x component with respect to time. So let's start with y. I know that y is 1/4 of t squared minus 4. Imagine if you distribute this 1/4, you would have 1/4 t squared minus 1. So then the derivative of 1/4 t squared would be 2/4 of t. 2/4 t would actually reduce to 1/2 t. So I think this is going to be 1/2 t. The second part of that, the minus 1, is actually going to disappear when you take the derivative with respect to time because we know constants have a rate of change of 0. How about for dx dt? So in this case, if this was t to a 1/2 over here, I know that the derivative is going to decrease it by a power. So I think we're going to have 1/2. And then since we have to knock it down by a power, this is already t to the 1/2. If you subtracted 1, you would get t to a negative 1/2 like this. So let's reduce it. We know this 1/2 divided by 1/2 is just going to be 1. So that's kind of friendly. And then here I have t to the first divided by t to a negative 1/2. Well, I know that if you have the same bases and you're dividing, you can subtract the exponents. So if I did 1 minus a negative half, maybe I'll write it here, 1 minus and then negative half, hopefully to agree that turns into addition. 1 plus a half is going to be 3/2. So I'm thinking that the first derivative is going to be 3/2. So then you could write it, dy dx is equal to t to the 3/2. Maybe we can also answer the question, what is the slope at this point 2, 3? But the only issue is that if we're looking at this first derivative, I have the slope generically in terms of t, but then notice the point that they gave me is rectangular. It has x, it has y, but if I want to find the slope, I would have to know something about t. So anybody have an idea how you might be able to discover what it is? Well, if you look at your parametric equations, the parametric equations say that we have a way to relate x's to t's and y's to t's. So if we know what x and y are, we could actually plug them in and then solve for t. And it turns out at this point 2, 3, whether you solve it in the y equation or in the x equation, the time value should be the same. So then I would say always default to the part that's going to be easier. Is it going to be easier to work with the equation for x or easy to work with the equation for y? I would hope that you would agree that it's going to be easier to work with the equation for x. Maybe it's not that much harder to work with the one for y, but there definitely would be less work in solving the equation with x and t related. So since I know x is equal to 2, I could plug it into the equation x equals the square root of t. So if I plug that in, 2 is equal to the square root of t. Hopefully to agree, you could square both sides and you'd be left with t is equal to 4. If I know t is equal to 4, I can now take this and dump it in and try to find out what the numerical value of my slope would be. So I would get 4 to the 3/2 power. Well, what is 4 to the 3/2? That's the same thing as the square root of 4 cubed. So in this case, I like to do the square root part first. So the square root of 4 would be 2, and I left with 2 to the 3rd, which is 8. So in this case, dy dx is going to be 8. I'm going to have a positive slope, which means the function is going to be increasing. So at the point 2, 3, it's increasing. If you look at this little picture that we have to the left-hand side, you'll see here's the point 2, 3. And if you look at the slope of the tangent line, you'll see that the slope of the tangent line is actually quite positive. It's increasing rather quickly, and that's exactly what positive 8 would mean in this case. Okay, so I've finished half of it. I finished like the slope part of the conversation. I would now have to talk about the concavity. I would hope that you would say the concavity is going to deal with the second derivative. And we know from the previous example, the second derivative is to take the derivative of the first one and then divide it by the original dx dt, or the derivative of the x component. Just because I'm going to move to the next slide, I want to make sure I identify it. We know dx dt from the first one we did is going to be this 1/2 t to the negative 1/2. So let's go after this concavity and see what happens. So I want to address this concavity part. So let's talk about the second derivative. So we'll use notation, d squared y over dx squared, and then equals, what's the derivative of the original one that we came up with? So we can say, what about d dt? And then we're trying to take the derivative of what we came up with a moment ago, which we said was t to the 3/2. And then we want to divide it by the original dx dt. So just like I did the last one, I'm just going to write it out with the notation. What's the derivative of t to the 3/2 with respect to t? I would hope you would say it's 3/2 t to the 1/2. Again, exponent comes down as a coefficient, and then you knock it down by a power, divided by the original dx dt, which we just said a moment ago is going to be 1/2, and then t to negative 1/2. So the first thing I want to address is going to be 3/2 divided by 1/2. I know that dividing by a half is the same thing as multiplying by the reciprocal, 2 over 1. So 3/2 times 2 over 1, the 2's are going to cancel, and we're just going to be left with 3. I would then move on to here. I know that if I'm dividing things with the same bases, I can subtract. So I'll have t to the 1/2 minus negative 1/2, which will turn into plus. A half plus a half is 1, so this would be 3 t to the first. So let's just write it here. The second derivative is going to be 3t. So now we want to know what is the concavity, again at the point 2, 3. We've already done the hard work to find out that at the point 2, 3, the parameter time behind the scenes is going to be 4. So all we have to do is just plug that in. So hopefully you'd agree that if I plug in 4, this will turn into 3 times 4, which is going to be 12. Of course, we know 12 is bigger than 0. What would be nice to know about the second derivative? Well, if the second derivative is positive, if it's bigger than 0, then what does that mean about concavity? I would hope you agree this means that the graph is going to be concave up. And if you look at our picture, would you agree that at 0.23, the tangent line is below the curve? By definition, that's exactly what it means to be concave up, is that the graph is going to be above the tangent line as you move away from the point of tangency. So in this case, I think we have it. We can say that the second derivative is this 12, it's bigger than 0, so we know it will be concave up. All right, so that's kind of a nice example. Example 2, it talks about the first derivative, it talks about the second derivative, doing some things with time in the background. Okay, so how about example 3? So example 3 is an old question with a new twist. It says we have this prolate cycloid, which is a fancy way of saying this little loop that we have here to the sides, and it gives us the parametric equations, y and x in terms of time. It says that the point crosses itself at the point 0, 2. Can we find some equations of both tangent lines at this point? So we need to find 2 equations of tangent lines. So that's kind of indicating like there'll be 2 separate ones or 2 separate slopes. So we can kind of see what happens. Okay, so the first thing to kind of consider is the points that we have. So we know the point that we have is going to be 0, 2. So that's kind of nice to know, is that if we're going to write an equation of a tangent line, we know that the equation of a tangent line is always going to be of the form y minus y1 is equal to m times the quantity of x minus x1. And if I want to write this equation, I need to know 2 things, a point and a slope. It seems like we have the point here, so the only thing I would have to go searching for are the slopes. So that would be something we should do. We would need to know the derivative, so that would be another thing. So maybe that would be the first place to start. So we could say, kind of jumping in, we know the first derivative is dy dx. We can take the derivative of each component separately and divide them. So let's start with dy dt. So what's the derivative of 2 minus pi cosine of t? So if we'd agree the derivative of 2 is going to go to 0, we know the derivative for cosine is negative sine, but then what if there's a negative pi out front? Well, negative pi times negative sine is going to be positive pi, and then sine of t. All over, let's go to the x component. Well, we'll start with this 2t. The derivative of 2t is going to be 2 minus, and then here I've got pi sine of t. We know the derivative of sine of t is cosine of t. So then negative pi times cosine of t is going to be negative pi and then cosine of t. So now if I want the slope, I know the slope is written in terms of time. I would have to go find out what the time values are. So in this case, I want to plug in this 0, 2 into one of these equations. Would it be easier to plug in for x or easier to plug in for y? Take a second to think about it. Which one should we plug in? Should we put 0 in for x or 2 in for y? What's going to be easier to solve? Well, I hope you said that we should plug 2 in for y. The reason why plugging in 0 in for x is that we have a 2t minus pi sine of t. So it's going to be hard to get t by itself there. So since we know that time value that we're solving for t is going to be the same in x or y, we just pick the one that's going to be easier to work with. So I would say let's plug in y equals 2. So if I plug that in, I'm going to get 2 is equal to 2 minus pi and then cosine of t. I can start doing some solving. So maybe I start by subtracting 2 from both sides. So I'm going to get 0 is equal to negative pi cosine of t. I can divide both sides by negative pi. So then I'll have cosine of t is equal to 0. Without looking at the unit circle, would you know some places on the unit circle where cosine is equal to 0? Well, I hope you would say that if we're looking at the unit circle, then the 2 places we're kind of interested in would be at the top and the bottom, so kind of like the North Pole and the South Pole. So what could we say about those t values? We could say that it's going to be at pi over 2. We could also say 3 pi over 2. We know pi over 2 is the guy on top, and then 3 pi over 2 is going to be the one on the bottom. Another way to say 3 pi over 2 is to talk about going in the other direction. Again, if I start here on the positive x-axis and I travel the way around, then that's going to be 3 pi over 2. But what if I wanted to start at the positive x-axis and then just travel the other way? Well, that would be the same thing as negative pi over 2. So if you wanted to, you could say this is also the same thing as negative pi over 2. So then if I know that these are my t values, then all I would have to do is just take these and plug them in and see what happens. So if I take them and plug them into dy dx, I should be able to say what the slopes are, and I should be able to write some equations. So that being said, let's take this derivative. I know that the point I'm going to be plugging in is going to be 0, 2. So for both of them, I should have something like y minus 2 is equal to the slope times x minus 0. We just need to find out two equations as to what this slope is going to be. And we want to plug in pi over 2 and 3 pi over 2. So, all right. So let's see what happens with it. So maybe we'll start with t is pi over 2. Again, I'm just having a fresh slide here, so I have some space to write. So then what about t at pi over 2? So if we take our derivative, we can actually plug in. So I'm plugging it into this guy right here. So I've got pi times sine of t. So this would be pi times sine at pi over 2. So if we find sine at pi over 2, I would hope you'd agree that that's going to be 1. So I'd have pi times 1 all over 2 minus pi. And then we had cosine at pi over 2. Cosine at pi over 2 is 0. So we could multiply by 0. We're going to be left with pi over 2. So in this case, we have our slope, so we could write the equation. We could say y minus 2, that's going to be the point that we had, is equal to the slope, which we know is pi over 2, and multiply by x, the quantity of x minus 0. So this will be the first equation of a tangent line that I have. I should also do this for 3 pi over 2, which you could write as negative pi over 2 as well. So I'm just going to write it as negative pi over 2. And if we find the slope there, we know that we're going to have pi. And then what about sine at negative pi over 2? That's going to be negative 1 all over 2 minus pi. Cosine at negative pi over 2 is also going to be 0. So this guy would also be negative pi and then over 2. So I have my slope, so I can take it and I can also plug it in. I know that my y coordinate is still going to be 2. I know my slope is negative pi over 2. And then times the quantity x minus 0 again. So that would be my second equation of a tangent line. And if you look at the picture that we have off to the right here, also on your paper, you'll see that we have these two tangent lines, and now we have the equations for them as well. Okay, so very good. That will be example 3. Again, as always, if you want to pause and take a look or talk about it, feel free. All right, the last thing to mention in parametric is to talk about arc length. So the first thing I want to ask you is, do you remember the arc length formula in rectangular form? Again, rectangular form is our standard form, and with y's and x's that we've been working with for the last several years. So if you want, you can take a second, challenge yourself to see if you remember what it is. So if you want, you can pause the video, or if people just want to dive in, we can. So what is the arc length formula? All right, as for arc length, I was hoping you came up with something like this. So the arc length is the integral of a square root of 1 plus the derivative squared. Oftentimes we wrote it like this. We said that it was the integral, and then obviously from a to b. But then we always wrote it as 1 plus, and then we would say like f prime, and then squared. But hopefully you'd agree that's the same thing as what this one is saying. It's just writing the derivative as dy dx instead of f prime. So if you go to your notes, you'll see that we can actually find arc length in parametric as well. So it starts kind of in a similar way. It says, well, here's the rectangular way of doing things, but we know that dy dx is the derivative. We know another way to find the first derivative in parametric is to take the derivative of the y component and divide it by the derivative of the x component. Then inside here, I've got 1 plus that quantity squared. Well, what if I wanted to add those two together? I would need common denominators. So you could write 1 as the quantity of dx dt squared over dx dt. They now would have common denominators, and you can add them. Well, then if you take a square root of that, you could actually take the square root of the numerator and denominator separately. And if you do that, you can do a little bit of algebra, and you'll find out that this is actually a really good working version of the arc length when you're talking about parametric. So all we would have to know is to find dx dt and dy dt components separately. The derivative of the components, we can actually just plug it in and then use the formula. So then we see in our notes that here's actually how they're going to define arc length in parametric form. You can notice it's not too crazy. It still looks kind of like the one for rectangular, but instead of 1 plus f prime squared, we're just finding the derivative of each component separately, squaring them, and adding together. So if you're getting vibes of Pythagorean theorem, then you're actually spot on. This has a lot to do with Pythagorean theorem, which is also true for doing it in rectangular form because we're doing it with the unit circle. So then last question here that we have in our notes that we need to complete is example 4. It says, can we find the arc length of this parametric curve? So it's kind of an interesting one. You can see it's parametric by the arrows that are there. This is called epicycloid that's traced by a point on the circumference. So we want to say, well, what's going to be the distance traveled in one complete trip around? But if you look at it, let's say we started right here. If I just found the arc length of just this piece, I can see that that's symmetrical to other pieces that are in quadrant 2, 3, and 4. So if I just found out what this arc length was in quadrant 1, I could multiply it by 4, and that would give me the arc length of the entire thing. So that's going to be our goal. We can say, using what we now know about this formula, we can integrate quadrant 1. We know quadrant 1 will start at 0 and go to pi over 2. And then if I can find out the derivative of the components separately, I can plug them in and then integrate it. We are going to integrate it using the graphing calculator. So a couple things that we'll need the derivatives of the components. So that should definitely be something that we write down. So maybe we'll start there. How about if we find dx dt? So dx dt, let's find that first. So the derivative of 5 cosine of t, we know the derivative of cosine is negative sine. So this will be negative 5, and this will be sine of t. Minus cosine of 5t. If I try to take the derivative of cosine of 5t, I'm going to run into chain rule. I know the derivative of cosine is negative sine. The derivative of the inside function is going to be 5. So I think this is going to turn into plus 5 sine of 5t. We can take the derivative of y with respect to time as well. So what about the derivative of the y component? Well, the derivative of 5 sine of t is just going to be 5 cosine of t. Again, if we try to take the derivative of sine of 5t, I'm going to run into chain rule. I know the derivative of sine is cosine, and then the derivative of the inside function is going to be 5. So I'm thinking this is going to be minus 5, and is going to be cosine of 5t. So if I know that, I can actually build a little integral. I can say, let's do arc length equals. Again, I have the integral from 0 to pi over 2. This would find me just the arc length in quadrant 1. And then I'm going to have a big square root. I know I need to take the components separately and square them. So then let's take the x component derivative. This was negative 5 sine of t plus 5 sine of 5t. And then we would square this component. And we can do the same thing for dy dt. I'm going to try to fit it in here. Hopefully I can. So how about 5 cosine of t minus 5. And then this is going to be cosine of 5t. And that quantity is going to be squared. And then, of course, dt to show that this antiderivative is going to be in terms of time. But if I've done that for quadrant 1, I know that I need to find the distance traveled for the whole entire thing. So then would it make sense to say that in quadrant 2, this distance would actually be the same as what we have in quadrant 1. In quadrant 3 would be the same. In quadrant 4 would be the same. So then what we can do is just take our integral and multiply it by 4. So in this case, I'd get something like this. So then let's take it into our calculator. So this 4 is by symmetry. So can I take it into the calculator? It's probably not something we'd want to do by hand. And let's find out what it is. So if you can pause the video, give everybody a chance to plug this into the calculator. And you can plug it in with x's. You don't have to plug it in with t's. You'll still get the same answer. So if you pause it, give everybody a chance. What's going to come back? I can definitely say that I was surprised the first time that I saw this answer. Okay, so I was hoping that you got an answer of 40. So in this case, the arc length is 40. Again, it's not terribly hard to calculate. It does remind us of the arc length that we did in rectangular. but there is another one that we have to know when we're doing parametric equations. We have to know how to find the arc length in that as well. So that being said, there probably is one more other one that we'll talk about in terms of arc length, and when we do polar graphs. So there'll be 3 total different little ones that look the same when it comes to arc length, depending on what kind of functions we're in, whether we're in rectangular, parametric, or polar. So, okay, hopefully at this point things are making sense. If the sub can tell you guys what the assignment's going to be, we'll kind of go from there. But in a nutshell, that's everything you'd have to know calculus-wise about parametric equations. All right, guys, I'm hoping that everything made sense here. If you have any questions, feel free to reach out to me. Hope all is well. Have a good day, and I'll see you in the next one. Bye-bye.